difficult. From your preview, you should have an idea about what the modulus function does. So, for example, if I wrote these down, you should be able to tell me what each answer is. So this one, the modulus of -4 is 4, the modulus of 5 is 5, and modulus of -7 is 7. So what the modulus does is if you input a negative value, it outputs the positive version. So -5 is positive, so it stays as positive. -7 is negative, so it gets outputted as positive 7. So what the modulus is doing is it's finding the distance of the number from 0. That's the official definition. That's how we can use it from vectors. So something like this vector here, that means what's the distance from this vector and 0. So that's when you would do plus 2 along, 3 up. So we use Pythagoras to get it. Yes, that's how these two lines, the magnitude, modulus, they're exactly the same thing. Okay, with that in mind, here, the modulus around the 5 doesn't really have any impact on the 5. So let's have a look at what the modulus does to functions, for example. So if I had modulus around the function x, well, I would need modulus around that, because I could put in -2, which would come out to be 2. I could put in -5, which would come out to be 5. So this would equal two things. It would either equal x if x is already bigger than 0, but if x is negative, then I'll have to times it by -1 to make it positive. So you would have seen that definition in your booklet and as part of the preview. Now there's some functions where by putting the modulus around it, it has no impact. So for example, if I did this, modulus x squared, well, x squared is always positive. Yeah, try something in a negative number. -1 squared is 1, -2 squared is 4. So therefore, I don't actually need the modulus brackets around it. I can just ignore it. That's the same thing as x squared. Yeah, that's important when we're doing integrations. You know, that sometimes we'll get stuff like this when we integrate the modulus brackets. However, if I had this, I don't actually need the modulus brackets. I can just put normal brackets. And think, why is that? X squared plus 1, again, that's always positive. It's never negative. So a quick way you can check is you just type in your graph x, I need an x first, x squared plus 1, draw it, and if I zoom out a little bit, you should see that I never actually, why is it being weird? You should see, look, that it never goes below 0. So there's my 0 line, look, and then the graph never goes below it. So I don't need the modulus. So have a think about these functions here. And think, actually, I'm going to change that one, plus 4x. Have a think, do we need modulus for all those, or can we get rid of them? So sketch them in your graph and see. So this first one, hopefully, you should see that goes below the axes, and you can easily spot that just by something 0. So that one, we do need the modulus. The next one, e of x. Hopefully you should know this one already. E to the power x is always bigger than 0. So therefore, we don't actually need the modulus around e to the x. And lastly, that one. So I'll put that one on to try and trick you, because it looks like we don't need modulus. It looks like everything's positive. So let's look what happens. It goes below the axis, so we do need the modulus for that one. Okay, just a couple more things before we get into the booklet. So the modulus is kind of like a bracket. So it's sensible to ask two things. Is this true? So to test it, let's try some numbers. So let's try 2 and 5. Well, 2 add 5 is 7, and the modulus of 7 is 7. Modulus of 2 is 2, modulus of 5 is 5, 2 add 5 is 7. So it looks like it works. Okay. Now we know that things might go with negative numbers, so let's try 2 add minus 5. Well, 2 add minus 5 is minus 3. Modulus of minus 3 is 3. Modulus of 2 is 2. Modulus of minus 5 is 5. 2 add 5 is 7, so that doesn't equal 3. So this thing here doesn't work. Yeah, I'm not allowed to split the modulus up if there's an add in the middle. Think what other functions can I not do that way? So lots of them. So lots of functions that I can't split up if there's an add. Something like this. Something like this. Something like this. Something like this. In fact, most functions can't split up if there's an add. Okay, and the second thing, then we'll get into the booklet, is this. Can I split up at times? So let's use 2 and 5 again. 2 times 5, does that equal that? 2 times 5 is 10, modulus of 10 is 10. 2 is 2, 5 is 5, 2 times 5 is 10. Okay, let's try a negative number. So let's do 2 times minus 5. Okay, so 2 times minus 5 is minus 10, and modulus of minus 10 is 10. That's 2, that's 5. 2 times 5 is 10. So it works. So this rule, in fact, does work. Yeah, so what this rule actually tells us is we can do stuff like this. If I have modulus of 2x add 10, I can factorize out 2. So I can write it like this. And we know that the modulus of 2 is just 2. So I can just simplify it to that. Yeah, and that would work with negatives as well. So if I was doing this, modulus of minus 2x minus 10, for example, I could factorize out a minus 2 if I need a modulus around it. And that leaves me with x add 5, and then that turns into 2. So these two things here are the same thing. But more of that later. Right, we're good. So we've had to play around with what the modulus means. So now we're going to have a go at sketching some graphs. So we're going to try sketching just y equals modulus of x. Okay, well, the way we do that, I'm hoping, actually I'll do, no, the graph's not big enough, I'll do it in here. You can still see this. The way one way of doing it is to sketch the graph without the modulus. So I'm going to sketch the graph y equals x, which looks like that. But we know the modulus, it takes any negative answers and turns them into positive. So this bit here gets reflected up there. So it looks like a V. Like that. And if you want to check in your calculator, the way you type it in is you go on options, go to numeric, and abs, because another phrase for modulus function is absolute value. And then you get your 2 lines. I'm just going to type it next. There you go. There's a V. Okay. Now this next one, I can do the same thing. modulus of x add 3. So I could sketch the graph x add 3. So something like that, where it crosses there 3. And then again, any negative bits gets reflected. So it looks like a V that's been moved along. Yeah, another way of doing that is use graph transformations. So if I call f of x modulus of x, then this thing here is f of x plus 3. And you know that that's a translation, 3 to the left. So that should be minus 3. The only bit you might have to work out is the y-intercept just by subbing in 0. So can you have a go at trying the rest yourself? So press pause, try them, and I'm just going to draw the answers on here. So this is f of x take away 3, so that's 3 to the right. And then sub in 0, so again modulus of minus 3, which is 3. This one is f of x take away 3, so that goes 3 down. So that one there is minus 3. Now this one here, actually D, I can't really draw the graph using that method where I draw it without the negative bit, because this minus 3 isn't part of the modular sign. Yeah, same with this one, and same with this last one here. So these ones here where there's stuff outside modular sign, it's probably best doing these transformations. So this one is, I can rewrite that as modulus minus modulus x plus 3. So that's minus f of x plus 3. So minus will reflect it, and 3 moves it 3 up. So it crosses there 3, and these numbers here will be minus 3 and 3. This one is f of, I'll write as minus x plus 3. Now this one, since it's owned modulus, I'd probably sketch the graph. So 3 minus x, well, it's a negative gradient, and it goes through 3. Get rid of the negative bit and reflect it up, so like that. So 3 there, 3 there. Now that's identical to that one. So think about what I said about factorizing. Think why they might be the same graph. Because this thing here, I can factorize out of minus 1 and be left with 3 minus x. And the modulus of minus 1 is 1. So they're the same thing. These ones, I will probably sketch the graph first and then get rid of the negative bit. So 3 minus 2x, so it crosses at 3, and it's a negative gradient. And this bit here is going to be 3 over 2. Get rid of that bit and reflect it up. So 3 over 2. And that, sorry, I could have written that as f of minus 2x plus 3. This one here, I could write this as f of 2x minus 3. Again, take a prediction of what this is going to look like if you haven't done this already. Since there's one modulus, I'm going to sketch the graph. Get minus 3 down here. And this is going to be 3 over 2. Negative bits gets reflected up. So minus 3 turns into 3 there. It looks just like that last one. I think why might it look like that last one? And then lastly, this one here, since there's something outside the modulus, I can't do this reflecting trick. So I have to use transformations. Well, it's just this one, so it's just edge. I'm just going to call that edge of x to be lazy, minus 1. So it's just this graph moved down by 1. So that's 2. And if I want these 2 points, I would just make this equal 0. And that's what we're going to do later on when we solve stuff. But instead, I'm going to show you how you can use a calculator. So it's 2x -3, with a -1 outside, draw it. And if you want those 2 points, remember G solve and then intersect. Oh, sorry, root, not intersect. That's when you've got 2 graphs. So x is 1 and x is 2. 1 and 2. Tells you that like x is 1, well, 2 and 1, 2, 1. A bit more playing around with some notation. So you know from geometric sequences that modulo signs or with inequalities can just be written as one inequality. So you know that modulus of r is less than 1. That's from an infinite geometric series. We can rewrite that as -1 is less than r is less than 1. Okay, and again with a binomial example. So you were doing stuff like 2x modulus less than 1. So you know you could write that as -1 less than 2x less than 1. Then divide it all by 2 to get that, which is the same as that, which is the same as dividing this first thing by 2. Yeah, but that's from the binomial expansion, remember? Okay, or we could think of it as vectors. So if I had a vector, take away a vector, and I had a magnitude or modulus, I can use that word now, around it, think what does that actually represent? Well, a minus b is the displacement between them, so that's a to b. And that means distance in vectors. So this means the distance between 2 vectors. So if I have this, for example, 2 take away 5, without doing any maths, I can think of this as what's the distance between 2 and 5? Well, it's 3. Let's check if that works using maths. 2 take away 5 is -3. Modulus of -3 is 3. It works. Okay, let's try this one. What's the distance between 5 and -4? Well, that's 9. 5 add 4 is 9. Modulus of 9 is 9. Okay, let's try and use this trick. If there was a plus in the middle, how would we do that? Well, plus, I can always write as a minus negative. So what's the distance between 5 and -2? 7. Okay, now we're going to try and use that trick when we have some algebra now. So we have modulus of x minus 5. So that means the distance between a number and 5 is less than 3. So if I was doing that one, I've got 5 here, and the distance between a number, so a number on this number line 5, is less than 3. Well, let's see what 3 would give me. 3 would give me 8 this way and 2 this way. And I want the distance between them to be less than 3, so that means my number is anywhere between here. So my number is between 2 and 8. And tomorrow we'll look at ways of solving inequalities like that. But today I just want you to get your head around how can we do it by thinking about distances, and it's just that. Okay, well here's an example. Write the inequality x plus 4 is less than 6 in that form. Well, x plus 4, I'll do this in a booklet. So x plus 4, I can rewrite that as x minus -4. So it's the distance between x and -4. So I'm drawing a line. Here's -4. And the distance is less than 6. Well, 6 this way will take me to 2. 6 this way will take me to -10. And I want the distance to be less than 6. So I want to be these numbers here. So I want x to be bigger than -10 and less than 2. Okay, I, the distance between x and 2. So here's my number line. Here's 2. And now I want the distance to be bigger than 7. So 7 this way, we're taking it to 9. 7 this way, we're taking it to -5. And now I want the distance to be bigger than 7. So I want to be past the number 9 and past the number -5. So I want my x to be less than -5, or I want x to be bigger than 9. Okay, and finally, this one here is giving us an interval and wants us to work backwards. So it's given us this thing here. That's what this interval means. It means it's between -3 and 7. It's in square brackets. That means it can be equal to. And we want to try and turn that into a number line so we can get a modulus. So -3 and 7. Well, if you notice, this number here is in the middle of these two. So what's in the middle of -3 and 7? It shouldn't take too long to spot. That's 2. Okay. And then how far this way to get from 2 to 7 is 5. And 2 to -3 should also be 5 hopefully. Good. So I want the distance between x and 2. And I want that to be less than or equal to 5. So my A is 2, my B is 5. Okay, so I'm just going to leave that there for a minute, and you're going to do some practice there. And then tomorrow we're going to look at how do we solve equations and solve inequalities.